Alright guys, we got a lot to cover here, so I want to lay out what we are going to do, and then uh, we will do it. Pretty straightforward, I guess. So what I want to do is I want to talk about 9.1, 9.2, and then get into 9.3 as much as we can. And then I want to talk about our lab that we got coming up on Thursday. It's a little bit more concrete than some of the labs we've done so far this year, so I hope it'll be a little bit more intuitive and enjoyable for y'all. I'm going to be posting some links for you guys to watch in preparation for it, and in addition, I will send you the lab sort of document that'll have some pre-lab stuff, and we'll talk about that a little bit at the end, so you can maybe make some notes. And I'm getting the sense, a little bit of discussion from various students about having some issues with some of this math, and so I want to work some problems from 9.1 and 9.2 and maybe in the 9.3, and then what I'm going to do is I have worked all of the homework from that was due today. So 1, 6, 9, 13, and 19. I've worked all of those step by step, not super broken down, but more than just the answer in the back of the book. And so you guys can rework those and figure out where your issue was or what you're not understanding. And then I want you guys to reach out to me. I'm going through you guys' homework, and often I'm grading it after we've already had a test on it or a quiz on it. And on one level, that's my problem. And let me be clear, on the first level, that's my problem. Okay, I need to get and stay current about getting your homework graded and back to you. But at the same time, if I send out a homework and the answers are like significantly different than yours, or it's work completely different, you guys have got to go back and check through and figure out where. I mean, that's the ultimate goal, is that you've got your homework and you've got my work, and then you're looking and you're going back and forth trying to figure out, okay, here's step A, and I was right there. B was right, but C, something went wrong. What went wrong? Oh, here's what went wrong. Now, why did I use that number, or Mr. Forster used this number? Oh, okay, I was using the wrong constant, or something like that. Okay, so I want you guys to, really start to engage with using your homework as a periodic check to your understanding. And to that end, I'm committing to make sure that I get you guys the full solutions worked out by me of any homework that we've got or that we've done. Okay, I did not get you guys that laser stuff very quickly. I think I got you all the answers for that. And I want to get, this homework that we're going to talk through a little bit was just due today, so I want to get that in your hands pretty quickly, so we don't get too far removed from it before you figure out what went right or wrong on your homework. Okay, so let's review where we are, where we've come to so far. We sort of had a little bit of an off day because of the quiz last time, and you watched our favorite YouTube chemistry guy, and he's good. But I want to talk through some specifics in the math and the solving and all that stuff. So let's just go through, and I want you guys to be cognizant of what we're talking about in each place here. Okay, I think we've got a math problem on a number of fronts. I see a lot of math errors, a lot of math confusion, both in getting word problems into the equations, to then solve, and then actually in the solving of the equations. So I'd say it's maybe 50-50 on what people are having trouble with. And so both of those are things that I want to help you guys and help you address and get better at. And then also we're having some trouble about content. I'm clearly giving you guys some information over various classroom periods. We may have 4 lectures that make up a quiz or test, coverage. And, I'm asking you stuff that's like directly out of the lectures, and you're you're just blatantly missing it. Okay, whether it's vocab or it's how to work something, or a lot of people had a lot of problems with the oxidation states. I get it. It's some of it's very tough, and again, I don't want to minimize that chemistry is a tough subject, but I feel like there may be some laziness on making sure you guys are recording and processing everything that's presented to you in class. Okay, I need to be able to be free to assume if I've covered it in a lecture and we've done a homework on it, then I'm free to test you on that. Okay, and that if you don't know how to do it, you need to first know that you don't know how to do it. And the way you do that is by checking your homework. And if you've got the wrong answer, figuring it out and emailing me. Okay, and again, I get maybe 1 or 2 people per assignment that tell me, hey, I'm a little confused on this. Usually it's one of maybe 2 or 3 students. And then we get to quizzes and tests, and things the wheels are kind of coming off for various people in various chapters. Okay, so this is not directed at anybody in particular. This is a class-wide trend, and I think we can just do better. I think y'all can do better. So to that end, I want to maybe review a little bit, give you some equations that are going to be important for this quiz, for this lab, for this chapter's test, and then let's get to doing some problem solving. I think we're probably just going to have a regular quiz here on the first part of this chapter. The lab's kind of throwing it off a little bit, and then we'll have a full test, I hope. I haven't actually planned that far out, so I'm not sure exactly when all this stuff is going to happen. So I've got to lecture 9.3 today on my planning document for y'all, and then we will, I guess, pick up with 9.4 after we do the lab. You guys have got a lab report we got to get in. I mean, we've got a lot of work to do, kind of right here before spring break. Okay, so without getting close to 10 minutes here, kind of just talking about what we're going to do, let's actually get in here and do some of it. Okay, so very quickly, let's turn to 228 in your books. Okay, and he derives in equation 9.1, 9.2, and then finally we get to 9.3, and that's what you need to know. Okay, you need to know equation 9.3. I'm gonna zoom in a little bit here, guys. Okay, make sure you guys are clear on what we've got going on. All right, excellent. So here we go. So we've got Boyle's law, and I know this is what we went over the other day, so forgive me if things, if this is not super exciting for everybody, but I want to be clear on what we're covering and then give you the tools to really do really well in this chapter. Okay, so we have V1 P1 equals V2 P2. Okay, and so again, these subscripts don't mean anything other than to label which ones. So this is the first state where we start our problem out, and this is the state where we end our problem. All right, and so we can see from the math here, if this is 10 and this is 1, and the pressure goes to 10, well, the volume's got to shrink to 1, because that would be 10 times 1 is 10, and 10 times 1 is 10. Okay, so this is an inverse relationship. As pressure goes up, volume goes down. Okay, and let's take a little aside here. We have this guy, which we've talked a little bit about, especially in your YouTube video there, on, what's today? Tuesday, so on last Thursday. Okay, all of these are subsets of this. And what is this? This is the ideal gas law. And it covers all of the other ones. Boyle's law, Charles's law, the other little derived things in here. They're all captured within this guy. Okay? All right, so we've got the math. What else do you need to know? Okay, you need to have an intuitive sense of what's going on in this equation. All right, so if we've got, let's say we've got a balloon full of air, not full of water. All right, it's got to be a gas. And we have it at a certain pressure. It's at atmospheric pressure. Okay? Then we increase the pressure. Let's just say we take that ball in our hands and we start to squish it. We start to mush it down like this. What are we doing? We're increasing a pressure and decreasing that volume. Okay? That's Boyle's law in action. Okay? And we're going to see that in our lab on Thursday. Okay? As we increase pressure, we're going to decrease volume. All right, so that's that guy. That's it. That's all there is. The rest of it is you're going to be given things and you're going to plug them in and solve for the unknown. Okay? Very straightforward algebra. Okay, so don't let word problems trip you up. All right? I'm going to give you some equations, and then we're going to pop back over here and we're going to work through some of these. All right? Charles's law. What is that? Okay? Where this one related volume and pressure, this one relates temperature and volume. Okay? And very simply, V1 over T1 equals V2 over T2. Okay? And this is a different type of equation because this is a direct relationship. As temperature goes up, volume goes up. Okay? So you've got a volume at a temperature. Okay? You've got a volume at a temperature. And if you increase that volume, the temperature goes down. Or if you increase the temperature, the volume goes up. Okay? And that's the hot air balloon example there. As you crank up that temperature, it goes up. Okay? All right. Then we come to a section we didn't actually really talk about. And so let's pause here a little bit, and we'll talk about this for just a second. There we go. All right, so we have standard temperature and pressure. Okay, and what does that mean? This is just a set of conditions that give us a little bit of shorthand, and this is often, so they'll say gas is at STP, standard temperature and pressure. Okay, so what does that mean? Okay, that means that we just have a set temperature of 273.15 K, which is 0 degrees C. Okay, and what's the pressure? Nice and simple, 1 atmosphere. And that's it. Okay, now there are, you could do the other equivalents. You have bars, you've got PSI, you've got all those other things. But whatever they are, they got to be equivalent. We'll go ahead and do this one. 101.3. I'm so old. Uh, 325 kilopascals. Okay, and as we'll see from your homework, the only thing that this affects is which of these guys over here that you use, which R you use. Okay. All right. So this is your standard temperature and your standard pressure, and that's it. That just gives you some values to plug into one of these equations, like the gas law. All right, and so I wanna think about this for just a second as we get. Oh, I'm sorry. Let me cover one little topic else here. Okay, so this is 9.2.2. I'm sorry. This is 9.2.2. This is 9.2.1. Okay. And also we have this. Let's look at this. All right, so what does this even mean? We got gauge pressure, we've got atmospheric pressure, and we've got absolute pressure. All right, so let's think this through. All right, so let's say I have well, let's just think about this. All right, so I've got a tire. Okay, and it's an awesome tire. All right, and I take a reading on my little nub right here. I know you all know how to check your pressure. And it says 44 psi, pounds per square inch. Okay? Well, out here, we got the atmosphere pressing in on this. Okay? We got the atmosphere pressing in on that. Well, what does that mean? It means that this gauge pressure is actually telling us that the difference between the pressure inside the tire and the pressure outside of the tire is 44 psi. So if we took this into space on a rocket ship, okay, and we remeasured that, I'm not going to look up what atmospheric pressure is in psi, okay, we would say that gauge now would read, let's say, 62 psi. Why? Because now there's no atmospheric pressure here. Okay? And if we took it down into the ocean, until we got a lot of water, this is water, and it's all pressing. Man, is it pressing. Ooh, we're down deep. The pressure's on. Okay? We might take that pressure right now and it might say 0 psi. Okay? And that tire would be getting squished. Because there's now no longer 44 psi. Oh man, I'm sorry guys. I'm drawing all over off the camera here. Okay? They might say 0 psi because now there's no difference between the inside and the outside of that tire because we've increased the pressure pushing in on that from the outside. Okay? So if you need to memorize this equation, that's fine. I don't think you should have to memorize it. I think you should understand that the absolute pressure has got to be made up out of the atmosphere plus whatever's reading on a gauge. Okay, and just if you need to, go ahead and memorize it. Okay, there's going to be some question that asks you about that. Okay, all right. All right, so we got PV equals nRT here. All right, and let's come on down here and let's talk a little bit about that. Okay. All right, so we know what all of these are. Pressure, it'll either be given to you or you'll be solving for it. Volume, given or solved. N, given or solved. R, we're going to look at all the other units here. And let's say that we're on page 235 now here. Let's say that you were given this in kPa. This was in liters. This has got to be in moles because that's what it refers to. They'll all have moles in there. And then this was in K. Okay, well, we need to come here on page 235 and go to that first one, and we would be able to say that this is 8.314 liters kPa mole K. Okay, and so what that does is that lets all these cancel out and just leave you with what you need to be left with. Okay? So what mathematically does this mean for problem solving? Okay, so we said, what do we call this? We call this a constant. All right? So if we're working a problem, and anytime we work a problem, we've got to be working in the same units from beginning to end. We can't just arbitrarily change units in the middle because that messes up all of our math. So let's take this, PV equals nRT. Okay, you will be expected to know that equation. So just say it to yourself as many times as you can. PV equals nRT. PV equals nRT. Okay? Easy to remember. All right, and let's solve it for R. So what do we need to do? We need to divide both sides by NT. Okay, that allows the n's to cancel out, t's to cancel out. So R is equal to PV equals NT. Okay, and we also talked about the other day, remember we talked about if A equals B, B equals C, then A equals C, right? All right, so if we come right here and we have, let's just call this R is equal to P2, V2, N2, T2. We'll call this 1, 1, 1, and 1. What are they both equal to? They would both be equal to 8.314, or whichever of these constants we would need to use. So if A is equal to B and C is equal to B, then A is equal to C. So what can we write? We can write P1 V1 over N1 T1 V2 V2 N2 T2. Okay? So this is the most general of all the gas solving equations that you might need to have. Okay? And if you'll look, I'll zoom you guys out just a little bit and see if we can't catch them all at once. Okay? So what do we have here? Come on, let's focus. There we go. All right, so we got PVNT, PVNT. Let's compare. V times P equals V times P. V times P is equal to V times P. Okay, same arrangement. Well, how is that true? How do we compare these two things? Okay, well, in this situation, this is a specific example of this in which the number of moles is the same and the temperature is the same. Okay, so if they're the same on this side and that side, they cancel out. Okay, so this assumes, and it often will say in the equation or in the problem, that the number of moles is constant, or it's in a closed container, which means that the number of atoms in there can't change, right? And the temperature is held constant, or it's allowed to come to room temperature, or something like that, which is science speak of saying N and T are the same on this side and on this side. Okay? Let's look at our other law, Charles's law. What is it? V over T is our relationship. Well, look, we got one of those here. V over T is equal to V over T. Okay? So we're not concerned. We're assuming for Charles's law that pressure stays constant. And the number of moles stays constant. So that goes away, and this goes away, and we're left with V over T is equal to V over T if we leave P and N the same. Okay? So what I want you to see, though, is that this is your most general equation. It can be rearranged to this, and then they can be set equal to one another so that you can plug in and solve whatever you want. Sometimes it'll look like this. Sometimes it'll look like this. But you can always get there from this. Okay? All right. So now, let's very quickly, let's look at 9.3. Okay, we got a little bit of stuff to talk about in there. And then we're going to solve some problems for at least 15 minutes. Okay, and I want you guys to be paying very close attention to how we solve those problems. All right, so let's talk about Dalton's law of partial pressures. Okay, so this is not complicated. I did not understand this in chemistry. I always thought there was this weird, crazy law. Okay, it's not. Okay, so let's read through it, and then let's talk about what it means. All right, so right here we're going to talk about what he just says. Okay, Dalton's law of partial pressure states that for a mixture of non-reacting gases, so basically, you know, if there's a chemical reaction going on, obviously this is not true because an H2 and an O2 might combine together into one mole, which is into one molecule, which is going to create a very different pressure situation. So we're just talking about mixtures of gases. All right. If you have a mixture of non-reacting gases, the total pressure of the mixture, PT, is the sum of the pressures that each gas would exert if it were present alone. Okay. So just think about, you've got 10 people in a train car, and they would have a certain sort of pressure, right? So like they might be pretty comfortable in that train car if there were just 10 of them. All right, so we can think of their comfort level as the pressure. And then we add another 10 people to it. So things are getting a little tight there. There's a big guy sitting right next to you, and he hadn't showered in a couple of weeks. So the pressure's mounting in there. Okay, so we've doubled the people. And then finally we add a third set of people in there. So we got 30 people, so the pressure is really high now. There's really too many people in here, okay? Well, if we had 10 people in one car, 10 people in one car, and 10 people in one car, they would all have a nice comfortable level of pressure, say 1. We put them all into one car, they all have triple the pressure, and everybody's super uncomfortable, and we could say the pressure might be 3. Okay, so they each bring that one amount of pressure into that car. Okay, and we just add them up. So if we've got a gas mixture that's half oxygen and half nitrogen, we know that oxygen contributes half the pressure and nitrogen contributes half the pressure. Okay? All right. So let's solve a problem with that. Is there any? Oh, yeah. Okay. All right. So let's very briefly. Sorry, guys. I'm just skipping over here. Why is this important? Okay. Well, it's important that if you do an experiment like this, you're heating this. Let's just say you're heating this. It's creating a gas, and that gas is pushing the water down out of this thing, this test tube that's inverted there. Okay, they're collecting this over water with this full of water so that they don't lose any of the gas to the atmosphere. Okay, we're going to do something similar to this in our lab, so pay attention. And then, you move this and you get these levels the same, and then you can measure this volume. And so in that way you can say, hey, look, I captured this amount of gas. Okay. Well, what's the problem, though. Okay, the problem is the gas collected in the collecting vessel, so this is a mixture of gas from the reaction and water vapor, which evaporates up into the collection vessel along with the desired gas from the reaction. Okay? So basically, anytime you are figuring out the partial pressure of your gas, let's say you're collecting pure hydrogen in here, you want to know how much you've got. Well, you've got to do PV equals nRT. Okay, say it to yourself, PV equals nRT. Okay? But what you've got to do is you can't take the P just as 1 atmosphere, because you've got to subtract out the water vapor partial pressure. Okay, and like he says right here, we got table A4. Let's see where that is. Okay, so we got the partial pressure of water. So let's say we're at room temperature, which is approximately 20 degrees C. Okay, so we've got 101.325 kPa total. Well, we need to subtract out 2.339 kPa, and you can see that that's our unit. We need to subtract that out, and the rest that's left is what you plug into your PV equals nRT to solve for how many moles of gas or whatever it is that you've got going on in there. Okay, whatever you're trying to solve for. Okay. Let's come back and work one of those if we have some time. We're already at 30 minutes here. All right, so let's pull out your homework. Now you've already turned it in, or you haven't, and you're getting a full credit or a late credit. You know, it doesn't. Whatever the case is that the ship has sailed at this point. All right, so let's just approach one of these and see how do we solve. Let's see what 13 was. Okay, great. 13 is an excellent one for us to work. Okay. All right, so the first thing we need to do is we need to make sure we're able to read this question carefully and then apply it into an equation to solve it. Okay, so let's figure out what are we looking for. We're looking for moles of methane, then kilograms of methane, density of methane, and then carbon atoms, okay? So in your mind, you need to be thinking a lot of unit conversion right now, okay? Which may make you sad or may make you happy, but that's the case here. All right, so now let's go through and let's define our variables. And when I say define our variables, I mean write down the letter that represents that variable, and then write what value is given to you in the problem. Okay? Tank of methane holds 1550 meters cubed. Okay, so what is that? Well, that's a measure of volume. Okay? And we won't do any conversions yet, not at this point. Okay, and it's held at standard temperature and pressure. And what does that mean? 273.15 K is equal to our temperature. And remember, our temperature's always got to be in Kelvin. Otherwise, your answers are completely bonkers. Okay? We said pressure. We don't know what unit we're going to need to use for that, but we're just going to go ahead and call it an atmosphere for right now. Okay, so again, what's our equation? PV nRT. What are we missing? We're looking for moles of methane, so this is what we're going to be solving for. We've got R, because it's going to be a constant. We've got T, P, V. So we've got everything we need, and we're looking for this. Okay, because they've asked us a number of moles. All right, so let's flip back here to page 235, and let's look at our options. Okay, Okay, so we can do either one of these in whatever we want, so that's not a problem. We've got a meters cubed. Okay. Atmospheres mole K. That's probably our jam right there, guys. Okay. Because we can easily get to atmospheres. We know standard temperature is standard pressure is 1 atmosphere. We're going to be in K no matter what. They're all K. You can see that. We've got a volume that's already in meters. I think that's our deal. Okay, so let's pick that one. And we'll say R is 8.206 times 10 to the negative fifth. And it wouldn't matter if we picked another one at all. Okay? You can see that the number is essentially the same. 8206, 8206, only the exponent's different. Well, that's because there are 1,000 liters in a meter cubed. So once we do that conversion, we use the different R, we're going to end up with the exact same number. No matter how you work it with whatever R, as long as its units match, then you're going to come up with the same answer after you do your conversions. Okay, so what do we have? We've got pressure is 1 atmosphere. What's our volume? 1550 meters cubed. What's our N? That's what we're looking for. R, we just said, was 8.206 times 10 to the negative fifth. And then T, 273.15, and that's Kelvin. Okay? All right. Now, I want you guys to look at this here. Okay? If you are having trouble getting here, that's math word problem comprehension practice that you need to do. If you're having trouble solving for N, that is algebra that you're having an issue with. Okay? So make note to yourself which one is your issue. Where do you get stuck in a problem? And then you know what you need to practice, and you know how to talk to me about what your specific problem is. And so maybe we can get you some practice or whatever. Okay? All right. So let's simplify what we can. Okay, so this is, and I'm going to drop my units just for the sake of space here. 1550 times 1 is 1550. All right, and I'm going to do 8.206 times 273.15. So that's 2.241 times 10 to the negative 2, I believe. As we go 1, 2, 3, 4, 5. Yep, 10 to the negative 2. Okay? Times N. Okay? Now what do we need to do? Okay? Think about what the next step's about to be before I do it, to make sure you know what I'm going to do. Now I'm going to divide both sides by 2.241 times 10 to the negative second. If you're putting that in your calculator and it's ever on the denominator, you want to do parentheses because otherwise it'll divide by this and then multiply by that. You want to do that as a package there. This cancels out. 2.241 times 10 to the negative second. All right, and then we put that in our calculator. Slowly we put it in our calculator. All right, and we get what? N is equal to 66,100 69,151 moles. That is our first answer. That's A. All right. Nothing crazy here yet. Okay, how many kilograms? So we're going to come over here just for some space. All right, so we need to get from moles to kilograms. This is 3 chapters ago. So 3 chapters ago. Okay. All right, so we have 69,151 moles. And what are we? It hasn't mattered yet, but we're doing methane, which you might have to look it up, and I would never expect you to just, kind of pull that out of your hat, all right? I'd tell you what it was in parentheses. Okay, we're trying to get to kilograms. Well, what's our conversion we have? We know 1 mole of CH4 is 12 plus 4 times 1 is 16 grams CH4. Okay, moles cancel out, leaving us with grams CH4. Is that what we're looking for? Nope, looking for kilograms. So we want to know that 1 kilogram is 1,000 grams, and that's our conversion. Okay, and when I did this, I got 1106.4 kilograms of CH4. That's B. Okay, so nothing in here is super scary. All right, you just got to break it down into little steps and make sure you know what you're solving for. All right, what's the density of the methane? Oh man, this seems like this is a crazy off-the-wall thing. We hadn't even talked about density. How do we get what the density is? Well, let's just look back in either our brains or our books. Density is the amount of mass in a particular volume. Do we know both of these things? We sure do. Okay, what do we know? We know a mass, 1106.4 kilograms. And do we know a volume? Yes, that was what we were solving using. The volume is 1550 meters cubed. Mass over volume. Okay, kind of a weird mass, kind of a weird volume. Okay, doesn't really matter. Okay, so we literally just plugged that straight in without rearranging anything. 1106.4 divided by 1550. And that's 0.714. 0.714 what? Kilograms per meters cubed. Which, if you do the calculation, also becomes 0.714 grams per liter. Okay? Both of those are acceptable. Liters, meters cubed. We could also take it to, milligrams per milliliter, milligrams per centimeter cubed, whatever, man. Okay? You get here, or here, or here, or here, you have 100 on that question there. Okay? So nothing crazy there. All right, and then finally, how many carbon atoms are in the tank? All right, how do we get to number of atoms? Okay, well, we know we've got 69,151 moles of CH4. And we know that 6.022 times 10 to the 23rd molecules are in 1 mole of CH4. How do we know that? Avogadro's number. All right, that doesn't quite solve it, though, does it? Because we don't want to know how many molecules of CH4, we want to know how many atoms of carbon are in there. Okay, so we want to say 1 molecule of CH4 has how many carbon atoms in it? 1 carbon atom. Okay, then you multiply that by that, and I did this already. Okay, I got 4.16 times 10 to the 28th carbon atoms. Okay. All right. So kind of, I mean, you know, that's not nothing here, guys. I mean, that's a good chunk of a quiz that we just worked through. All right, and you know, as the more you do them, as you do them more, you will get faster. Okay. But I have, like I said, I worked all of the stuff. I will take pictures of those and I will upload them just as soon as that homework gets turned in, which obviously for me it's Monday night, and you guys are watching this on Tuesday morning, so hopefully I will have uploaded this. Okay. I feel like that maybe is a little bit helpful for some of you and maybe slow for others. So, you know, this is a great opportunity to bear with one another on something like that. Okay, so what we'll do is that's going to give us enough to where I think we're going to have an opportunity. Let's see. Trying to think about what the best use of time is here. All right, so that's your homework. Let's get that out of the way here. Okay. All right, so in theory, we're all the way up through 9.3. I want to talk to you about your lab. Okay, so what are we going to do with the lab? All right, so we're going to do both Boyle and Charles' law. Okay, both of them are going to be, we're going to do one on one half of the experiment on one. We're going to have to do half the experiment on the other. And you're going to need to be able to use both of these equations to predict what's going to happen. And then we're going to do the experiments and compare what actually happened with what we predicted. Okay? Because that's where we seem to be getting a little bit stuck in our thinking, is comparing the actual to the theoretical, which was, I don't know if it was a conceptual problem or I just didn't work enough of these or make you guys work enough of them. I just, I'm sorry, because I think about half of y'all missed this. So just as an aside here, when we're talking about percent yield, okay, anytime we're talking about a percent, generally speaking, in the world, you're talking about the part out of the whole. Okay? And in our case, the part is what we actually got. And the whole is what we predicted we would get. Okay? And this can also be written actual over theoretical. And so just again to clear this up, this can be more than 100% because you can do a bad job drying your sample and you end up weighing water, or you can have a contaminant where oxygen comes in and oxidizes and adds its mass. Okay. So if we predicted 75 grams of product, that's our theoretical. Okay. But we only got 74 grams of product, which is actual. All we do is plug it in. 74 over 75, and that'll give us our percentage. Okay? And you literally divide one by the other. All right? So this becomes 90, well, we get 0.987, which to get a percentage, we 98.7% yield. Okay, let's not ever miss that again. Okay, it's going to come up because we're not done with stoichiometry yet. Because as you can see in 9.4, we're going to end up doing the stoichiometry of gases, which is just like what we did before. So it's not anything super new. It just has one little added layer where we're talking about gases, and so we talk about volume. So what to look for here? I think I'm going to have Miss Barron work through the rest of these homework problems with you. I think that would be most helpful. And then I'll also send them to you so that you can, if you don't want to, ask in class or whatever to slow down the class, that's perfectly all right. But then I'm gonna send you these other ones here, and so you can see what you need to do. You can see I need to clean this guy up a little bit. Not particularly pretty there. If I have time, I'm going to rewrite it. If not, you're going to have to struggle through my stuff as well. I've got to finish writing y'all's lab. So y'all work through the rest of these. Really, take the rest of the class and dig down and figure out if you got questions on some of those. Make sure you've got your homework out while you're doing that and are correcting it. You don't have to turn the corrections into me, but it'll be helpful for you to correct it yourself. And then tomorrow, you need to be looking for a lab sheet. You need to be watching the YouTube video that is linked. There are actually maybe two, depending on whatever. There'll be one or two YouTubes, neither one of them very long, but they're going to give you the general idea of what we're doing in these labs. Okay? And then we will pick back up. I've got to do some more planning here, but we will pick back up and figure out how we're going to fit in lab report, spring break, the rest of Chapter 9 quiz, and all of that. Okay, so on to y'all's homework. Work through those. If y'all are doing it right, it may take you 5 minutes per question, so you may not get through them all, but again, you'll have them all to you so that you can work through them on your own. Okay, guys, communicate with me. Let me know what I can do to help. If you have specific questions, let's get this knocked out. I really want us to just I want to zoom in on this lab report and really communicate well between me and you so that you can understand what I'm trying to get you to do, and that we can end up with everybody getting an A on this lab report, because it's a test grade, okay? And I think there's not a student that couldn't use a good test grade at this point. I'm not trying to be mean about that. We're doing a lot of work here, and there's a lot of new concepts, and so we just need to keep working hard. We are about to finish up our 6/8, so that's great. That means we are 3/4 of the way through the year. Okay, you can do anything for the last quarter. Okay, you can run that last quarter mile. It's not a problem. Okay, you just gotta put your big boy and girl pants on, and you just gotta do it. Okay, so let's work hard, and I will see you guys soon.